Hello, Chemistry 11 honor students. This is lesson number 2 in regards to the atomic emission spectra. So today what we're going to do is just finish off the notes that I gave you and finish off talking about electron configurations and just some things that you should be aware of. Okay, now remember last day, my video wasn't working very well, but remember we ended off here where you were taking a look at the electron configurations. And the idea was to fill the electrons from the lowest down from the nucleus, and you fill it up, filling the lowest energy levels first. And what you would get is you would get something like this, 1s2, 2s2, and so on. Couple of things for you to be aware of. This is not English. Please do not put commas. You do not put commas like if you were listening. It's like you would think of this electron configuration like a complete name, okay? So you don't put commas in. Now, if you take a look at germanium with 32 electrons, it got pretty long, 1s2, 2s2, and so on. So is there a shorter way to actually do it? And the answer is yes. Now, if you take a look at your periodic table, okay, what you will notice is that the periodic table is actually separated into different sections, okay? The first two columns, you fill this as the S block. The last 6 columns, I'll put this in a different color. This is the P block. And in the middle, what you have here, this is the D block. Okay? Now, here on the left-hand side, the 1, 2, 3, 4, 5, 6, this is the energy levels. Now, in terms of the energy level, the D block is 1 energy level less. Now, so this is actually kind of ingenious in terms of how you can do this in the short notation. Now, let's take a look at calcium again. Remember calcium, we had the 1s2, 2s2, and so on. Is there a way that we could use this to shorten up our message or the electron configuration? The answer is yes. So if we take a look at where calcium is, calcium, notice I've highlighted in blue, it's in the 4th energy level, 1, 2, 3, 4. So what that means is that it ends at 4s2. Now, an easy way to go through this is instead of starting right at the very beginning, right at hydrogen, where we do 1s1, 1s2, whatever, what we do is we look for the noble gas that's before the calcium, in this case, argon. So what we do is we just write, we just write square brackets argon 4s2. That is it. How do we get 4s2? We start here, and then we just jump. Oops, did something happen with my computer? It jumps 1, 2. Okay, so that is how it goes. So if my pointer doesn't work right now, so we go 4s1, 4s2. Okay, so that is how we could do it, the short form. Now, how would we do germanium? Okay, so germanium is right here. Okay, so germanium is right here. Again, so germanium, so what happens is we take a look, we start back at argon, so we do square brackets, argon. Yeah. Don't tell me my pen is running out of charge right now. Okay, so sorry about that. So we start off with argon. Okay, and then we come here, we go 1, 2, so it'd be 4s2. We jump 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 3d10, and then 1, 2, and then that would be my 4s2. Okay, well, 4p2, sorry, 4p2. And so instead of writing out what we did last day, where we had the 1s2, 2s2, 2p6, 3s2, all that sort of stuff, this first set is replaced by a noble gas. Okay? Now, what is the significance of this? So with this new model, when we say valence electrons, electrons in the outermost shell, it includes all the electrons in an atom except for those in the core notation. So core notation, another name for this would be noble gas. Or in a completely filled D or F subshell. So let's say, for example, in this case, completely filled. Now, so let me give you an example here. So let's say if we were to look at let's look at sulfur. So let me give you a straightforward example first. So example, sulfur. Okay. Sulfur, if we were to do this, it would be 1s2, 2s2, 2p6, 3s2, 3p4. Now, this 2s2, 2p6, this would be my core notation. Why? Because this is a filled S and P of the same level. Okay, so core notation. And so the number of valence electrons would be this one. This would be my valence. And then I would have 6 electrons. Now, you might say, well, Mr. Chan, how is 1s2, 2s2, 2p6 a core notation? Because if you look at the electron configuration of that, 1s2, 2s2, and 2p6 is the electron configuration of neon. So if we looked at this, we would write again, here would be square brackets, neon, 3s2, 3p4. Okay, so again, here you have 6 electrons, valence. Now, what if germanium? So let's say for germanium, remember it was argon, 4s2, 3d10, 4p2. Now, because the D is completely filled, this is filled, we don't include it. So it's filled. So the key word here is filled completely. So it is not valence. Okay. Now, because of this, so therefore, the number of valence would be 4 electrons. Why? Because it came from the 4s2 and the 4p2. Okay, so that's talking about valence electrons. Now, when writing electron configuration for ions, okay, negative ions is easy. Add electrons to the last unfilled subshell, starting where the neutral atom left off. So let's say we had fluorine. Fluorine is 1s2, 2s2, 2p5. Fluorine minus 1 would be 1s2, 2s2, 2p6. Now let's say fluorine is minus 2. It'd be 1s2, 2s2, 2p6, 3s1. Notice I added to the new energy level. The reason being is because the p orbital can only hold 6 electrons. Once it's maxed out, you have to start a new row. Now, for positive ions, it's a little bit different. Electrons in the outermost shell, or the highest energy level, are removed first. Now, let's go back to germanium. Okay, or let's do germanium here. So let's do germanium. Remember, it is argon, 4s2, 3d10, 4p2. Oh, actually, no, let me do something different here. Let me do a different one here. Let's erase that. So sorry. So let's say if we have scandium. Scandium is argon, 4s2, 3d1. Now, if we had scandium plus 1, you would have argon, 4s1, 3d1. Notice the electron was removed from here. Removed. Now, the question is, why did we remove it from the 4s1 and not the 3d1, Mr. Chan? And the thing is this, you could say, isn't the 3d higher in energy than 4s? Oh, sorry. But yes, but 4s is the higher energy level. Okay? It's the higher energy level, so it is considered to be further away. Okay, so it's the energy level. All right. Now, so let's say, for example, what do I mean by the other one? If electrons are in the s and p. So let's say if we had aluminum, it is neon, and we have 3s2, 3p1. If I did aluminum plus 1, it would be the 3s2. Here, the electron is removed from this p orbital. So here, electron removed. Okay. Now, when an element and an ion have the same electronic configuration, they are said to be isoelectronic. So let's say, for example, we have fluorine minus 1 versus neon. Now, fluorine minus 1 would be 1s2, 2s2, 2p6. Neon is also 1s2, 2s2, 2p6. This is isoelectronic. Now, be very careful. Some of you might say, oh, Mr. Chan, all we need to do is look at the number of electrons. Yeah. The answer is no, no, no. Let me give you an example where I can trip you up. So let's say, for example, we have calcium versus, let's say, scandium plus 1. Now, calcium has 20 electrons. So I'm just going to give you the short form, argon 4s2. Now, for scandium plus 1, it also has 20 electrons. But notice it is argon 4s1, 3d1. This is not isoelectronic. And again, it has to do with where for a positive ion, where is the electron removed? It's removed from the highest energy level. Okay? Now, and remember, combining capacity is the number of electrons an element gains or loses to get a full s and p orbital in the outermost energy level, or valence shell. Now, combining capacity, you could think of this is like an ion charge. So let's say, for example, you have, let's say, oxygen, or let's say fluorine. Now, fluorine versus fluorine minus 1. So fluorine is 1s2, 2s2, 2p5. Fluorine minus 1 is 1s2, 2s2, 2p6. Notice, if we take a look at the S and P of the highest energy level, or the valence shell, I get a total of 8 electrons. And this goes back to when you did the Bohr model of wanting 8 electrons in the outermost shell. So this is how the wave mechanical model and the Bohr model are actually related. Okay? Elements in the same family have the same number of electrons in their valence shells. So, for example, so let's say if we had lithium versus sodium versus potassium. So lithium versus sodium versus potassium. So lithium, if I did the short form using the noble gases, it would be neon 2s1. Sodium would be, oh, sorry, that's not neon, it's helium 2s1. Sodium would be neon 3s1. And potassium would be argon 4s1. So notice you have same number of electrons in the valence shell. Okay. The last one is this, electron configuration exceptions. Up to the element chromium, there are 2 electron configuration exceptions. So when we did copper and chromium, up to the element of krypton, there are 2 electron configuration exceptions. Okay? You will notice the difference between here and here. So notice this one and this one and this one. Why? You know, it's hypothesized that a filled, not tilled, a filled or exactly half-filled d subshell is very stable. Therefore, an atom that is 1 electron short of a d5 or d10 may have an electron configuration in which 1 electron is shifted from the filled s subshell to having the highest into the unfilled d subshell. Now, what do I mean by this? So let's say for chromium, if we were looking at this, you know, we looked at our electron configuration. So this would be 4s. This would be like 3d. And remember, we would have, you know, 3p down here, 3s. We go like this. Okay, this is what we would predict. But through experimentation, they theorized that it actually looks like this. We have our 3s, 3p, this is also 3p. We would have our 4s, and then we would have, so it would look something like this. So what you would have is you would have this last shell. This would be filled. Now, why did they theorize this, or how did they come up with this? It has to do with how chromium was actually, and how chromium and elements like it actually bond with other elements. And we'll fill that in later on. Now, there is this quantum numbers. Okay, you don't need to know about quantum numbers. Okay, you don't need to know about this n or magnetic quantum number or whatever. All you need to know is how to do the electron configuration and how you are able to recognize valence electrons and some of the characteristics and the notes that I've given you here. Okay, so that will be the end of electron configuration. What I will be doing is I'm going to ask you to do the electron configuration worksheet. I would like you to do numbers 1 to 3, the odd letters. Okay. All right. So that is it for electron configuration. So hopefully you go through this and things make sense. And we will go over any problems you might have a little later on in our video conference. Okay, thank you very much. Have a good day.